Great. So first I will start with the basic revision of the entire thing I have done. Just 1 to 2 minutes revision, okay? So that you feel the connection with what I'm doing. So so I will draw, I love to draw, maps and stuff. So I will just started with this. So initially I started with some examples, okay? That why matrix is important, and I try to understand and give motivations for vectors, okay? So I try to make you understand vectors well. And then after that, I moved ahead to show you that how the notion of um, the vector space, like the mathematical abstraction part. Then comes the mathematical abstraction part, and then we define something called vector space. That we did in the first week. So math abstraction. So why we did it? Because so that it can encompass a large amount of examples, a lot of examples and different paradigms. For example, you can combine probability with linear algebra just because of like, vector space. If there was no vector space, you couldn't have connected this thing. So those are read articles they can understand. So a lot of examples and connections. After all, it's all about connections that happen. That is beautiful. Okay. So I remember a story. Someone was saying that. So there was a person who was in his entire life was um, a pilot. Okay, and he used to fly planes. And he was asked. He wrote a book, and in that book, or in some interview, in that book, he wrote that in an interview, someone asked him, what did you get? When did you feel the most happiest when you were flying? And he gave me a very simple answer that when there was another plane that another aeroplane or another pilot who was flying beside him, and they used to swing the wings of the plane, and that's like their the plane's way of greeting each other. So why I shared this stuff is that it's human beings always love connections, okay? So whether it's human connection or mathematical abstraction connection, so vector space helps us to connect, or deep abstraction, mathematical abstraction helps us to connect to a lot of different seemingly not connected topics, even though it's hard, symbols and stuff. But after all, human beings get excitement out of doing this, just due to this that they can connect a lot of seemingly undifferent, not disconnected things. Okay, so the examples, and then we understood vectors, and then we understood vector spaces, and then we moved ahead to understand that. So there was the next question that to understand a vector space, we should know what it is made of. So we went on to understand and discovered subspaces. So what are vector spaces made of? How actually the how are vector spaces made of? Okay. And then the next portion was, so using this results, using these two ideas, we understood how to show a vector space, how to show V is a vector space. And we have spent an entire week on this, okay, with assignments and stuff in the first week. That was the first question we addressed. And then after the subspaces, so the question is that, so we asked various questions. How do subspaces look like? How do vector spaces look like? How do subspaces look like? This was the first natural question. So the next natural question was also, how do the subspace interact with each other? Like, for example, in the assignment was given intersection of two subspaces was another subspace. So that was the idea. People are trying to understand subspaces and how two subspaces can give more subspaces. The goal was to understand the vector spaces by understanding its subspaces. That's it. If we understand all the subspaces of a vector space, then we can understand the vector space well. That's it. Okay. we understand it very well. So how do subspaces interact with each other? That there was some exercises on that. This was the goal. And then the another goal was so now people are going upside down, trying to break down subspaces. Okay, here they were trying to break down subspaces. Now they thought of a constructive way. They thought, can we create subspaces from nothing? So can we create subspaces? So it's like what I'm sharing to you is like an overview. Okay, I hope you have heard the famous quote by Steve Jobs that we always connect the dots backwards. So I'm just helping you to connect the dots backward. That how the whole thing are connected together. Although it didn't seem in the first place, but the idea is that how we can create subspaces out of out of a few vectors. Can we create subspaces? And that was the birth of span. Okay. And this changed the life of vector spaces. Because once we entered span, then we asked various things. We asked the things that span was, span, right? So then we asked that, can we find a set of vectors? Can we find a set of vectors that can span the entire vector space or the entire subspace or vector space? And the result was what? What was the result? Anyone? What did we get?
Basis.
We got the generating set. Okay. So we are trying to find a set of yeah. So you're right in some sense. We got basis, but we will break it down even more. We got generating set. Now, when we had generating set, the issue was that you have seen this that. So in this, we learned the problem solving step that how to show it's a generating set. Okay, we have issued this problem. How to show it's a generating set. We have this was the problem solving stuff that was in this week 2. How to show generating set. I think we did some geometrical aspect too. How to show generating set. But the next question was, people were, redundancy. The idea was that, many vectors were there which were not redundant. So it's like they were linearly dependent on each other. Also, while defining span, they also define the definition of linear combination because that comes inherently with the span. So then when they started addressing the concepts of generating set, they discovered that generating set was, there were too many vectors in generating set. There were too many vectors. So they thought of this that can we reduce? So the question was of redundancy. Redundancy. That means can we reduce the set? So what do we mean by reduce? What do you mean by redundancy? What they mean was that using using a few vectors, you can generate the other. The other vectors are also in the span of the rest of the vectors. So the idea was that the vectors are linearly dependent. So then came the idea of linear independence. Because they were trying to reduce the number of set of vectors which can generate. Okay, what is the minimum element in a set of vectors that can generate? Why? Because it was becoming redundant. The vectors are not important. It was becoming redundant. So then came the linear dependence and independence. My handwriting is very bad because I have to fit in all these whole things into small places, and I don't have a very sharp pen nib. So that was the idea. Redundancy. Okay, can we remove the redundant variables, vectors? And that was the final transformation. And these two things, span and linear dependence, gave rise to the basic idea of basis. That means the best set of vectors, the redundant the minimum set of vectors that can generate a vector space. So basis and dimension. So this was the goal, and then we also saw that how to show linear independence. We solved this, and that was there's a basic definition, and then linear independence is easier to show. Okay, generating set we saw, and then finally we did basis. How to show it's a basis. How to find a basis. We will do more. How to find a basis and how to show a basis. This was the two questions. These were the two questions. Anything else? So the idea was that the span and linear independence were opposites of each other, I told. Because if you increase the elements in the span, they will become linear dependent. And if you decrease the element in a set, they may not be span of each other. Okay, I mean may not span the entire vector space. So they are in some sense pulling each other apart. Okay, they are opposite forces, and the middle where it's stabilized, that's the basis. Okay, this was the base. This is the entire idea of vector spaces. Okay, that we have learned till now. Any doubts, guys? Did you understand all of this? I hope. Can you connect all these things together now? If yes, write an yes. If no, please ask me questions. Okay. What about others? Very good. Super. Preeti, Ron. Yeah. Okay. So as I told last day, Preeti, I will show you. One second. Let me open the last day's notes. And if it's there or not. Let me check. I think it's there. If you remember this diagram, then if you remember, I have showed that if if you increase, imagine this, Preeti, that if you have a set of vectors, okay, if you add more vectors to it, add more vectors to it, add more vectors to it, at some point it will become span, right, of the entire vector space, because we are adding more vectors. That means if you increase the number of elements in a set, that will become a span. But if you remove the number of elements in a set, but if you increase the number of elements in a set, that may become linearly dependent, right? Understand?
Yes, sir. Yes, sir.
Yeah, Preeti? You're telling me something? Hello, Preeti?
Yes, sir. Am I audible?
Can you hear me, Preeti? Yeah, Preeti, go ahead. Okay, okay. So that's the idea, that they're opposites of each other. Okay, that was what I wanted to share. So this is the entire set. So what's the next step? So we have now understood that what is a vector space and what are the atoms of a vector space. So we know this. The next question, the next idea that we will focus on is the following, that how, how do a vector space transform into another vector space, and why we're interested in it. So till now we addressed this question, that what is a vector space. The next question is that what are vector spaces, what are the atoms of vector space, and the fundamental elements, I mean. Now we will discover something else now. What something else we will discover? So let's go back to the first thing that we started with. So let's take this equation. Okay, let's take this equation. A x, or let's say 0.71x minus 0.71y is equal to, let's say, 5. And the next one is 0.71x plus 0.71y is equal to, let's say, 7. So now we have seen two geometries of it. One is row geometry. That is line and intersection of lines. We have some column geometry. Now we will address another type of geometry. That is transformation geometry. And this gives rise to, so it's like, you know, a single equation is giving rise, so this gave rise to coordinate geometry, coordinate stuff. The row geometry gave the coordinate geometry. This gave rise to the ideas of vector spaces. And you will see this gives rise to the idea of transformation, you will see. The same thing giving rise to 3 different aspects. So we have done this, we already know this, so let's discover this transformation geometry. What is this transformation geometry? So let's rewrite the entire equation in a very different manner. Or let's rewrite that using the things we know. Remember, we can rewrite this as 0.71 minus 0.71, 0.71 times 0.71, not times, sorry, times this matrix xy is equal to 5, 7. So we have seen it's nothing but summation of these vectors that is a column geometry. But what is this? A new idea of geometry is the following. It's as if, observe that I have told you this before. This matrix is nothing but acting as a function. You put in a number, you put in x comma y into this machine, and it outputs what? This matrix times this A times this x comma y. A new set of vectors. It's taking in a vector and giving out another vector in some other dimension. It may be here 2, but it can be any other dimensions also. The idea was, so let's now observe it very carefully. Let's now see the geometry of this transformation. What do I mean the geometry of this transformation? Let's go here. Okay. So let me share this tab with you and come here. Can you see this, guys? So observe. So forget about this, okay? Forget about what is this blue thing and stuff. But observe this is a matrix. And I will show you that this same matrix is actually something really interesting. It's actually rotating the entire space. So I will just set it and I will go. It's rotating the entire space by 45 degrees. I'll show it again. This matrix is nothing but taking x comma y and changing it to a 45-degree angle. For example, it's changing this vector, this black vector. Observe it's rotating it by 45 degrees. Everything. It's rotated by 45 degrees. Okay. So this is the geometry. This is the geometry that this transformation geometry is I am telling you. It's beautiful, right? Let's dive into this more, why this is happening and how this is happening. Okay. So for that, we need the technology to understand what is a linear transformation. Also understood this, guys, that why we are learning this? Because there's another dimension of geometry, transformation geometry that is happening to a matrix. You're putting in one x comma y and it's outputting, giving the output of another x star comma y star, and that x star comma y star in this case is nothing. So it's going from x comma y to x star comma y star, or you can say xa comma ya under this transformation. And this is nothing but the, one second, this is nothing but the rotation. This xa comma y is nothing but the rotation of this by 45 degrees for this a. Rotation anti-clockwise. How? That's a different thing. I'm coming to that later on. But that's a rotation. All of you understood this, guys? So there are other examples also. You can see over here, you can actually rotate, reflect, scale, shear, project, anything you can do actually by linear transformation. Okay, and we will explore them one by one, step by step. But therefore, that's the next step of understanding. Let's move ahead. Okay, so let's start. So what is a linear transformation? That's the next natural question. What is a linear transformation? So what is this? What kind of transformation is this matrix transformation? So observe this matrix transformation. Let's take a matrix. Let's take a matrix A. Okay, let's take M cross N. So observe when a matrix is multiplied with a vector. Okay, the vector must be N cross N, and the output Y is in M cross N. So a matrix is nothing but it's transforming R to the power n. It's taking a vector from R to the power n and keeping it in or moving it into R to the power m. Okay, it's taking a vector in R to the power n and moving into R to the power m. Okay, how? Where a of x is a function, a of x is defined as a matrix multiplication. You know, this multiplication. A times x vector. This is the definition. So now, the next natural question is that, what is very special about it? What is so special about it? What is so special about this? Let's see. The idea is that, you know, when you see this transformation, guys, when you see this transformation, you know, the origin is remaining the same. It's not changing. Origin is remaining the same. So therefore, we will see that matrix multiplication, this A, observe this, that if you multiply with a zero matrix, the A of a zero vector is always, so here we are taking a zero vector in n to the power 1, n cross 1, and we are getting an output of 0 of m cross 1. Don't get the dimension wrong, because it's from m r to the power n to r to the power m. It's taking a vector of 0, 0, 0 n dimension to, it's getting an output of m dimension. It's getting a zero vector. Also, there's a linearity in it. That means a linear transformation is, that means it preserves the linearity. It preserves the zero, it exactly preserves the properties of a subspace. It preserves the geometry of a vector space. That means it takes 0 to 0 and it takes any alpha times x vector plus x1 vector plus x2 vector. It's take alpha times a times this. It takes to what? It's A alpha, A times alpha, that means alpha A x1 curl plus A x2 curl. That means what? Alpha times A x1 plus A x2 curl. That means what? That means it preserves the linearity. Okay. If you have x1 here and x2 here, when it's transformed to ax1, ax2, I have told you this before when I was teaching you isomorphism. Let's say this goes to x1 plus x2. Then this also goes to the place where these two are going. The same place. That is ax1 plus x2 is equal to ax1 plus ax2. So here this gets added to this, and here this goes to ax plus x, and both are same. That means it preserves the linearity, and same goes for multiplying by alpha. I just wrote it in a same place. So that's the basic idea. That's the basic idea. That, oops, sorry. Oops. Oh, I have got it back successfully. Yeah. So that's the basic idea. So it preserves the linearity of the vector space. Also understood this, guys? Everyone understood this idea? Very good. Yeah, it's okay. Yeah.
Okay. So, okay, I am getting echo. There is some problem at it. Hello.
Yeah, hello.
Yeah. So, isomorphism, we discussed that. As you told now, if we have two vector spaces V and W, and they are isomorphic, that means there must be some linear transformation that transforms V to W, right?
Yeah, but here it's an isomorphic. I have not added the condition that f is on 2 or 1 1. So here observe that if a takes all the values to 0, okay, then also it's a linear transformation. If it takes all the values to 0, then also it's a linear transformation.
Yeah, my question is next. मतलब जाने अभी तक.
Please go ahead.
Yeah. So does this transformation have to be unique, or it can be anything, or there can be many different transformations which can connect two isomorphic subspaces? Sorry, two isomorphic vector spaces.
I'm not getting you. Which transformation?
There is some echo. There is some problem at my end. I'm not able to hear you properly.
Oh,
I'll ask you later. There is some problem.
okay.
Sir, I guess she's trying to ask that the linearity, like this linear transformation, is that unique for every vector x?
Define the linear transformation here. Okay, I've defined that. What is how is the matrix behaving. So I will now take this motivation to define the linear transformation. Okay, and then I will come to that question. I'm just sharing the properties that what is so special, what is this matrix doing, and then I will share the properties that comes naturally to, you know. So that's what my next idea is, that I have not defined what is a linear transformation right now. So now I will define a linear transformation. So what you saw is the matrix is transforming. So can we generalize this idea of matrix? Idea of transformation from one vector space to another. And that's the question. That question is lying in the idea of linear transformation. The transformations that transform one vector space to another, okay, preserving the linear property. Remember, if you take a function, R is a space, right? So R to R, let's take a function f. If you take f of x is equal to x's cube, okay, then observe that f of x plus y is equal to what? X plus y whole cube, right? And f of x plus f of y is x cube plus y cube. So also these are not equal. That means and it's one and onto. Every point is one and onto. Okay, it's a bijective function, but it's not linear. The linearity is not maintained. Okay, it's transforming one vector space to another, but here linearity is not maintained. That means that set of vectors it is transforming to, it's not behaving linearly. Here it's not behaving linearly. So here the linearity is not preserved. Although it's transforming one vector space to another. R is a vector space, right? So therefore the question is that how do we define so that linearity is preserved? So T is a vector. T is a function. T is a function from V vector space or W vector space. So we say that it's a vector space if first of all, number one, the number one criteria is that the linearity should be number one criteria is that it should go to 0, okay, and the linearity is preserved. So two criteria are there. So you can just sum it up in one criteria. There is T of alpha times x plus y, or x and y are vectors, is equal to alpha times T. So both are over R, okay, real numbers. The alpha is a real number, that's what I mean. Tx plus Ty. Even alpha is 0, that means it's 0. Okay, it's a 0 vector because alpha times a vector is a 0 vector. So 0 times a vector is 0 vector. So therefore we get that this is the only property, and observe that everything is managed in this. So this must hold. So if you have to show one is a vector space, you must show this. That's it. Remember that both the things are clubbed together. The multiplication by a scalar and multiplication and addition of vectors. Both the things are clubbed together in a single form. So this is what a linear transformation is. It preserves the linearity. Okay, that's it. It preserves the linearity. Okay, and observe that if you want to show one is not a linear transformation, you can show that T is not equal to alpha. T of 0 is not equal to 0 because because it implies that T of 0 is equal to 0. Okay, that is one very obvious output. Also, T of the negation, T of the negative vector is equal to minus of the negative vector. Okay, it's very easy because T of V plus T of minus V is equal to what? T of 0, right, is equal to 0. So therefore what? T of minus V is nothing but minus of TV. That means the negation of this, negation of TV. That means the inverse go to inverse and 0 go to 0. Therefore, certain good properties are held. Okay, certain good properties are held. The question therefore next comes that we have seen a matrix as a linear transformation. So how, the next question that we should address is that it's a new type of thing, right? T. So how we can define T properly? Like how can we understand T to the fullest? How we can visualize T to the fullest? How we can understand or visualize T? That's the question. And that's where the question of SK and Yogita comes, that we will see this, that every linear transformation every transformation can be expressed as a matrix. As a matrix. We'll show this. Okay, we will understand this. How? We'll see how basis of a vector space plays a very important role in this. And that's a unique matrix. Unique. And we'll show how to identify that matrix. We'll show that carefully. We'll take some examples now. But before that, tell me, did you understand the definition, guys? Any doubts till this point of time? We'll go into some definitions now. We'll go into some examples now. Okay, did you understand? Yes or no? No? We'll now go into some examples. Yep. Okay, great. Neha, Shinjini, Vaishnav, Aniket, SK, Priya, Kriti. What about others? Shaumya understood. Yogita, did you understand? Priyani? Very good. Okay. Great. Dhruva, Aniket, you understand? So now let's go back. Let's fall back on the examples of linear transformation. Let's see them. So let's see. So I will do some exercise problems so that I can share you some exercises. So this is some exercise problem. So T is defined from R cubed to R3. This by this. So that T of x1 comma x2 comma x3 is equal to x1 minus x3, x1 plus x3, x2, x3 minus x2, and x1 minus 2x2. Okay, this is how it's defined. Let's first prove that it's a linear transformation. It's very easy to prove. So what will you do? It's like alpha times x1 plus x2 plus x3 plus y1 plus y2 plus y3. Let's see where it's going. Let's see where it's going. It's expected to go. It's expected to go where? It's expected to go T of this. So the outcome is what? The outcome is nothing but alpha x1 plus y1, alpha x2 plus y2, and alpha x3 plus y3. So when it's going, it should be, if you apply T on it, then it will go where? Alpha x1 minus, sorry, I made a mistake. So yeah, alpha x1 minus x3 plus, so it's a big thing, so let me write it smaller. Alpha x1 minus x3 plus y1 minus y3. X alpha x1 plus x2 plus y1 plus y2, comma x3 minus x2 alpha x3 minus x2 plus y3 minus y2, comma alpha x1 minus twice xy1. Sorry, alpha x1 minus twice x2. Okay, it's becoming bigger. Let's write it off properly. So alpha x1, x2, x3, y1, y2, y3. So let's see where it's going. So t of alpha x1 plus y1, that means we are doing this. T of x plus y. We are seeing where it's going. It's going to t of alpha x1 plus y1, this vector, comma alpha x2 plus y2, alpha x3 plus y3. This is going to what? This is x1 star, this is x2 star, this is x3 star, right? You can imagine where it should be going. It should be going to alpha x1 minus x2 plus y1 minus y2. Alpha, actually it's a big one, x1 plus x2 plus y1 plus y2. Alpha x3 minus x2 plus y3 minus y2. And comma alpha x1 minus twice x2 plus y1 minus twice y2. And therefore, if you separate it out, you will get alpha times x1 minus x2, comma. If you add it out and separate it out, alpha x1 minus x2, comma x2, x1 plus x2 plus x3 minus x2 plus x1 minus twice x2 plus y1 minus y. I think this will be 3. Yeah. So I'm dot dot, and you can understand this is nothing but alpha px plus y, like p of y. Also understood this is a linear transformation. Did you understand that? The calculation seems very simple. Others, did you understand? Let me know yes or no. Very good. Okay. So let's solve this problem therefore. So t of 1 comma minus 2 comma 3, can you tell me where it's going? You can understand. It's x1, x2, x3. So if you put 1 here, minus 3, 1, minus of minus 2, plus of minus 2, comma x3 is 3, minus of minus 2, x1 is 1, minus of twice minus 2. So you can understand where it's going. It's a new vector. It's minus 2, comma, minus 1, 3 plus 5, and 5 again. It's going to this. Find a vector so that t of x is equal to 8, comma 9, comma minus 5, comma 0. That means it's asking that x1 minus x2, x5 minus x3 is equal to 8. x1 plus x2 is equal to 9. x3 plus minus 2 is equal to minus 5. And x1 minus twice x2 is 0. And you can easily solve this equation now because these two are in x1, x2. So you can find x1, x2 from here. and you can replace a 2 and 1 here to get x3. And I hope they will be, you know, they must be coherent. Okay, they must be coherent. So of course it's going from one dimension lower to one dimension higher. So some possibility may not be happening, or it will not be, on 2, because it's going from lower dimension to higher dimension. So some possibilities must be there. So you can see that there are 3 variables and 4 equations, so it may not be solvable always. There may not be existent, a solution. So that's the thing. That's the question. So therefore, this is an example of a linear transformation. Okay, everyone good with it, I guess. So let's move ahead to the next portion. This is a linear transformation. It's done. Everything is done. So let's move ahead with another example. I think another example. Okay. So let's go on with another example. But let's try to understand this example in a different way. Let's try to see that this transformation, if you observe this transformation well, you can actually see something. It's actually asking that if you ask whether the tx is equal to y or not, it's indirectly asking that x minus 1 minus x3, x minus x1 minus x3, x1 plus x2, x3 minus x2, and x1 minus twice x2 is equal to y1 is equal to y2 is equal to y3 is equal to y4. If this is what is asking. So observe that maybe you can transform, it's a linear equation, right? So maybe you can transform in a matrix format. So let's try to form in a matrix format. Observe that, let's try to write in a matrix format. x1, x2, x3. And this is a matrix format. It's asking whether it's y1, y2, y3, y4. So observe it's a 1. For x2 it's 0 and there it's minus 1. Next one, 1, 1 and 0. The next one, x3 minus x2. That means 0 minus 1 because minus 1 with x2 and 1 with x3. And the final one, x1. So minus twice x2, 0. Therefore, this is a linear equation. This T is nothing but equivalent to this matrix. T is nothing but equivalent to this matrix. The question is that is it the case always? All of you understood this idea? All of you understood this? That what we are going ahead, that a matrix linear transformation that is defined like that actually can be expressed in the form of matrix. So the question is that a linear transformation is actually equivalent to matrix in this sense. The question is, the further question, the in-depth question is that whether every linear transformation is a matrix or not. All of you understood this idea? Great. Super. Soumya, did you understand? You're joining in and out, so maybe there you have some problems in the net. Great. Super. So therefore, the thing is that if I ask you, so you saw the rotation. The question was, there are two questions. When it comes with a definition, okay, the question comes that how we can break down, how we can represent a linear transformation? Rather, how another question is that how can we like it's like when we still represent, it's like how we can represent a vector space. It means that how we can break down a transformation into smaller pieces and understand it. Another question is like breaking down, it's like destruction. Another question that naturally comes is construction. How we can construct a linear transformation. How we can construct a linear transformation. And both of them have the same answer, and that will be going to next. So both of them are the same answer. So remember, like it was the same thing as the vector space. Both of them are the same answer. That was the basis. Here, it is a matrix. And let's discover this now. Why it's a matrix? How it's a matrix? Sure. I hope all of you know the definition of 1, 1, on 2, and bijective, guys. Please say yes if you know the definitions of 1, 1, on 2, and bijective. Okay, great. So I'm not revising that. Observe that I will know, okay, before going into the next matrix, I will show you some examples. Another example. This connects real analysis and linear algebra. See, I always love connections, okay? Because I believe everything is connected to everything else. Every subject is connected to everything else, okay? And that's why I know statistics is a one way of that. You know, you can use statistics to understand music, you can understand literature, you know, there's natural language processing, you can understand. I was like, there was some, you know, Mohallavish Olympia that we held, and people gave me different things. It can be used to understand nature, you know, geology, weather. It can be used to understand astronomy, okay? There is astronomical data science. You can use to understand anything, like anything in the world. Okay, statistics is all about data, so information can be used to understand everything. Okay, just about everything. So therefore, statistics in some sense is the connection between each and every science. Okay, also it's a connection between mathematics and science in some sense. So connection is everything. Okay, and therefore I love connections. That's why I will share this example with you. So we already know a vector space that a set of all f from R to R such that f is differentiable. So it's a vector space, you know that, right? It's a vector space. I have discussed it. Now, what I will do is that I will define a transformation from V to V itself. So let's take, yeah, or let's take, not V itself, I should say, let's call it infinitely differentiable. Infinitely, like it's like any derivative is exist. So observe it can form a function from a transformation from this to this, such that any p of f is f dash of x. So any p of f is f dash of x. Okay. Observe, let's prove that this is a linear transformation. And you know that if a function is f dash of x, same, it does not mean the function are same, because f of x plus 1 and fx both have the same derivative. equal up to, it's equivalent up to a constant. But observe, let's try to observe it. So first thing you should prove that P of any alpha f plus g is what? Alpha f dash plus g dash, which is equal to alpha P of f plus P of g. You can understand that this is the linear transformation. So you can say that derivative of a function is nothing but a linear transformation from a set of all functions, infinite differential functions, to the set of all infinite differential functions. It's like a transformation of vectors. So this gives a different idea altogether of derivative. Okay, so this is the connection, but you cannot go farther from here and go something, but yes, you can go things deeper, and yeah, you can go things into very deeper things. For example, you see that power series actually, okay, so let's see if I can share that afterwards, but this is an example. Okay, I hope all of you understood this example, right? Yeah, all of you understood this example. Yeah, it's okay.
Hello.
Yeah, please go ahead.
Yeah, am I audible properly?
Yeah, you're audible, but if you hear it echo, it's nothing to do. Okay, you have to talk, even if you hear it.
Yeah, okay. So is this the reason why we made this matrices, right? Convergent plus convergent, series is convergent, or continuous plus continuous function is continuous. That those matrices look very similar because all of them are linear transformations. Is that the reason?
What are similar? Can you talk a bit slowly?
I just can't hear anything. I'm sorry. There is some problem.
Okay, I will write down. You can hear me in the class, but you cannot hear when you're speaking, right? Okay, I don't know what is the issue. Let me just check. Can you check if you can hear me now? Can you unmute yourself?
Yes, I can hear you now. I can hear you now, but
Can you hear me now? Like,
yes, I can hear you now, and I don't know. There is no echo now.
okay, good. Please go ahead with the question.
Yeah. So we made those matrices, right? Continuous plus continuous is always continuous function, and differentiable function plus differentiable function is always differentiable function. And all those matrices look similar. So is it the reason behind it is because all of them are linear transformations?
Um, no, no, that are not related to linear transformations. Yeah, it's a different thing. Yeah, or just let me think. No, they are not related to linear transformations. Yeah. There was also multiplication of functions, so that is not related. That is not related to linear algebra.
Yeah. So because of that, it is not related to related.
Yeah. So yeah, so you are asking another question before. Was that clear? That uniqueness or something?
Yeah, my question was is the linear transformation unique, which is equivalent to the matrix? Is it unique?
So I will show that. Okay, I will show that. Yeah. So therefore, this is done. The next, try to understand whether we can express a linear transformation in terms of a matrix or not. So linear transformation and matrices. So let's try to understand only from R to R to the power n. Okay, Rn to R to the power n. Otherwise, it will be a bit hard. All these things geometrically. So let's just understand Rn to R to the power m. Okay, we'll not go into general things. it may become a little bit overwhelming for you, and that's why I'm not doing it generally. But let's just do it for Rn to r to the power m. Okay. So let's just check. The idea is that, let's say Rn has a basis. The most easiest basis of Rn is what? 1, 0, 0. It's called the Euclidean basis, okay? 0, 1, 0, dot, dot, dot. The basis of r to the power is the most usual basis. Basis of r to the power n dimension, n cross 1. Similarly, basis of r to the power m is 1, 0, 0. It's m cross 1. M elements and n elements in each one of them. So now let's just observe. Let's just observe something. So observe that we are telling what? We are telling that t of x, t of alpha x plus y, this is going to alpha of tx plus y. This was a linear transformation where it was starting from. So now natural question is that, we can express this x in terms of the basis, right? So let's call the basis e1, e2, dot en. That means you can write it as summation of, or you can write it as alpha 1, or you can write x1 e1 plus x2 e2 dot plus xn en, right? So you can write yn yi as y1 e1 plus y2 e2 plus dot yn en. Now let's take a transformation on here. So alpha times this will nothing but alpha times alpha x1, alpha x2 dot alpha xn, and if you add this up, you will get alpha x plus y is nothing but alpha x1 plus y1 e1 plus alpha x2 plus y2 e2 plus alpha xn plus yn en, right? I apply the transformation on here. So you get nothing but, observe that since this is true, so therefore it's nothing but alpha x1 plus y1 times t of e1 plus alpha x2 plus y2 times t of e2 by the properties of the linear transformation. That's what alpha xn plus yn times t of en. So what does this give? What does this tell you? This tells you that any vector can be uniquely written as this. So this tells you that if you know that t of e1, t of e2, dot t of en, that means where the basis elements are going. Then you will know everything about t. The question is that if you know where the individual basis elements are going, then you will know everything about t, just about everything. Why? Because you will know where t of x will be going, right? You know that t of x will be nothing but x1 times t of e1 plus x2 times t of e2 plus dot xn times t of en. Now x1, x2, xn are are corresponding to x vector. So the xi's are fixed. So therefore, if you just know t1, t2, tn, that's done. That's done. Did you understand, all of you? Do you understand that if you know where the transformation of basis is going, then you know the entire thing? Did you understand this, all of you? This is very important. If you know where the individual basis elements are going, then you know everything about T. Okay? Others understood? Very good. Superb. Great. So we will use this small, basic, very basic idea. See that how the basis actually operate in the entire vector space. So if you know the transformation of the basis, you know the entire thing. Okay, that means we just need to understand how the bases are transforming. So using this principle, we will construct the matrices. We'll see the little transformation. So observe that T of any x vector is nothing but what? T of x1. So T of any vector. So if you observe it, like if you write it in this term, that T of any vector x1 comma x dot xn, you can write it as T of x1 times this 1 0 0 0, that is e1. So you get what? You get x1 times t1 e1 plus x2 times te2 plus dot xn times ten. So observe that you can write this as, so this is a vector, right? This is a vector. Remember, this is a vector. This transformation is also a vector. This is the m-dimensional vector, since t is going from Rn to R to the power m. The m-dimensional vector. That means also you can write this as, if you arrange this as Te1 matrix, Te2 matrix, Te3 matrix, like vector, sorry. You can stack all these n matrices down. You will get what? You will get m cross 1
n cross n matrix.
Yeah, m cross 1 stacked n times, so you get m cross n matrix. You multiply each one of them with x1 or xn, you will get nothing but the same equation. For example, just like the row view, 0 1, let's take, I'm revising 1 second, 2 3 times 4 5 times x comma y. The matrix, this is a column view. Okay, this was a column view. It's same as x times 2 3 plus y times 4 5. It means you can imagine this is like this times this plus this times this. So this times this times the next one, this times the next one, and this times the next one. That is multiplied and added here. Added. So therefore, observe any t, if you can express in this, then you can form that. So therefore, what is the matrix corresponding to a t? You have a t from R to the power m to R to the power n, R to the power n, R to the power n to R to the power m. You find out where the individual 1 0 0 these are going. Let's say this is going to xi1 vector in our m cross 1. T 1 0 1 0 0 is going to xi2 vector. Dot T 0 0 0 1 is going to xin vector. So what do? You stack all of them down in row columns. Okay, and that will be your matrix corresponding to this transformation. Okay, so now let's see some examples before moving on. Let's see some examples. So let's see some examples. So first example, we have seen the rotation is a matrix. So therefore, rotation is a linear transformation. Rotation by, let's say, theta degree. Understand this very carefully. This is very important. Anti-clockwise. So let's take this. So let's draw a diagram. First, this is an application, so remember this. So it's very intense. Please focus, okay? So what it's telling, if you want to understand the matrix of this transformation, this is transformation, this is transformation, okay? So why this transformation? You can easily understand if you have a matrix this, if you add it, like if you have a matrix this, and if you scale it, it will rotate at the same angle. And if you have if you have a vector and you scale that vector, that will, if this is rotated by theta degree, that will also rotate by theta degree. And if you have two vectors, this is rotated by theta degree, and this is rotated by theta degree, then their their addition is also rotated by theta degree. Therefore, this is a linear transformation. You can see geometrically. You can prove it after all later on, but that's not that's very easy to understand. The question is that using this technique, you can actually see, you can create a new transformation. You can, in fact, you can create any transformation. Just define where the 1, 0, 0 and 0, 1, all the E1s, EIs are going, and that will create any possible transformation. Okay, so therefore this answers our question here, that how we can represent linear transformation by a matrix, and how we can construct a linear transformation. So using the basis thing, we can construct and represent both, and we'll see this example. So represent the matrix of this, okay, theta degree anti-clockwise transformation. So by the rule, we just need to know where 1, 0 is going and where 0, 1 is going. Why? Because this is a transformation from R2 to R2, right? We just need to know where 1, 0 is going and 0, 1 is going, because basis has two elements. So let's see where 1, 0 is going. There is 1 comma focus, okay? There is 1, 0 here, this vector. It's rotating by theta degree. So what will be this point? Can anyone tell me by trigonometry? The x-axis will be what? The x coordinate and y coordinate. The length is 1, you can see. The length is 1. What will be the x coordinate? Anyone? What will be the x coordinate of this? When it rotated anti-clockwise by theta degree? It's a vector of length 1 whose angle with the x-axis is theta. So what will be the x coordinate?
Tan theta.
Tan theta.
Cos theta comma sin theta.
Very good. Cos theta comma sin theta. Because this is cos theta, like base by hypotenuse is cos theta and height by hypotenuse is sin theta. So cos theta and sin theta. Right? So therefore this is going to cos theta comma sin theta. And let's take 0 comma 1, where 0 comma 1 is going. Yeah, anyone? SK, yeah.
You have written that on x-axis it is 1 comma 0. I guess you wanted to write cos theta comma 0 in the diagram on x-axis.
It's 1 comma 0. Yeah.
Okay, so it is ahead. It is after that point. Huh?
I'm not getting your question.
No, let it be. I got it.
Okay, so now let's take the 1 comma 0, 0 comma 1. It's anti-clockwise by 0 comma theta. So observe that, yeah, it's anti-clockwise 0 comma theta. So let's see that. So it's theta here again. Let's make it a bit larger. Now can you tell me what is this? 0, 1. So this is going to theta. So therefore this height is what? This height is sine theta, right? And this height is cos theta. So therefore the x-axis will be minus sine theta because it's negative, and the height is cos theta, right? Comma cos theta. Y is cos theta and x-axis is minus sine theta. Therefore you get this is going to minus sine theta, comma cos theta. So what is the matrix transformation? So first where 1, 0 will be putting. So the matrix corresponding to this rotation is cos theta, comma sine theta, and this is minus sine theta, comma cos theta. Can the person mute, please? Whoever mic is on. Okay. So this is the matrix of terrain. So let's represent it by this format. All of you understood the matrix building step, guys, of this rotation? So if you remember that for theta is equal to 45 degree, we get what? 1 by root 2 minus 1 by root 2. Yeah.
No, I was answering that question.
So can you find out the value of 0.1 by root 2 in decimal? Yep. Root 2 is 1.414. I'm asking 1 by root 2.
So 0.7 something. 0.7.
Please
0.71.
tell me the two decimal places.
0.71.
Very good.
That's what we started with, right?
Yeah. No, that's what we will end with too. So, I love to write things, okay? So, I love to write, and that's why I write a lot on LinkedIn and stuff. So, once I, took a short course on, how to write, how to be a writer. There are a lot of free courses available. So, in that course, one important present, like, how to be a storyteller rather, okay? So they have studied a lot of beautiful writers out there in all over the world, and they observe one pattern is that great writers, or if you I also love comedy, okay? I know if you don't know the comedian and the stand-up comedian Biswa. Do you hear him, Biswa? Anyone know of Biswa? No one watch stand-up comedy? Okay, great. So if you know him, he has a course, okay? Front row, I think. He's a comedy course. I took that comedy course, okay? And in that also, the same thing was told. And it's also the same thing that was told to me in the course of storytelling, that, wherever you start, there you end. It's like a joke in a full circle. I don't know if you observe this, but if you have observed stand-up comedian, let's say they pick up. I don't know if you have watched people's crowd work. Okay, I love the crowd work aspect. And if you watch the crowd work, you will see that they take a person and they grill him or her, and then they move on to the next person, and next person tells something, and then they connect it to the other person. So I remember that once that India wala guy did that. Uh, one was a shipping ka business, another one works in Ola or something. So they like connected each other. I mean, I'm not being able to tell the punchline. I mean, tell the whole thing in the perfect way. But the idea is that when a good thing is always ends in a circle. Okay. So whether it's a story or a comedy or life, anything. So therefore, I wanted to end it in a cycle, but I will do something more, of course. So that was the idea. So if you see this transformation, this was rotation by 45-degree left, anti-clockwise. So this is the idea. Yeah, Rahul Subramaniam, you're right. You're so right. Rahul Subramaniam. It's beautiful. He is a great person. He's a YouTube channel called Random Cheeky Bum, so you can watch that if you don't know. So yeah. And if you can connect linear transformation to stand-up comedy, that's when you know that your learning is successful. Okay. Great. So everyone understood what I taught you today till now? Any doubts till this point of time? Great. Super. So let's move ahead to the next part. So we have understood rotation by theta degree. Okay. So what we have learned today, we have learned the following thing, that what is the linear transformation? And linear transformation has an intricate relationship with the matrix. Every matrix is a linear transformation, and every linear transformation is a matrix representation. So let's come back to this example where we took, and we found a linear transformation in this way, right? So let's do it in a different way now. Let's take this transformation again, and let's do it in the way we have done it. So if you observe it, let's try to find it from R3 to R4. So we therefore need to find out T of 1, 0, 0, T of 0, 1, 0, and T of 0, 0, 1. So that's x1, x2, x3. So observe that if you put 1, 0, 0, that means 1, 1, 0, 1. The next one, 0, 1, minus 1, I think minus 2. Let me know if I do some mistake. Minus 1, 0, 1, 0. So let's write the matrix down. Therefore, first stack this one, T of E1, that is 1, 1, 0, 1. The next one is 0, 1, minus 1, minus 2. The next one is minus 1, 0, 1, 0. Let's check that with what we have done. I will copy this. Hope it's correct. If not, then I've done some calculation mistake. It's 1, 1, 0, 1, 1, 1, minus 2, and minus 1. Very good. So it's the same thing. So therefore, this is how you represent a linear transformation in a matrix format from R to the power n to R to the power m. Remember, the note is that you're only using the basis of Euclidean space, the Euclidean basis. Okay. If you take a different basis, the transformation will be different. The picture will be different. Okay. You have taken the 1, 0, 0, 1. If you have taken some other basis, the alpha i's will change. This alpha i's will change. This x i's will change. Okay. And the transformation will change also. The x i's will change and transformation will also change. So the matrix will also change. The transformation will be the same, but the matrix will change. So Therefore, that also comes like when two transformations are actually same, but their matrix representation are different. We will see that. Maybe not, but that's called similar matrices. Okay, we will see. But this is the idea that we're only using the Euclidean basis for the matrix representation. Remember that. This is very important. Okay, this is very important. So all of you understood this, guys? Any doubts till this point of time? I hope no. No doubts. I hope all of you understood this example too. Let's see what we can do more. Let's do a problem. Let's do a different kind of problem. Yeah, Shaumya.
How will we get the answer to part A?
Part A?
I just want to confirm. Yeah.
So part is t of x1, x2, x3. So you put it in here. I did it here, na? I did it here, na? You just put in the values of x1, x2, x3 in the corresponding place and you will find it. Did you understand, Shaumya?
Yes, sorry, I'm having a bad.
You're not able to?
Yes, sorry, I'm having a bad connection today. No, I'm sorry, I'm having a bad connection today.
Okay. I hope you understood this. Like, great. Okay, so let's do something that we will do next. So we understood what is a linear transformation, how to create a linear transformation, a matrix representation of linear transformation. But the question is that, we have understood the matrix. So therefore, we have got the matrix representation, but what's next? The next portion is that understanding what the linear transformation is doing. And we'll see the eigenvalues and eigenvectors we will do soon is mostly about that. Understanding what a linear transformation is doing. Understanding the linear transformation. As I told, when a linear transformation is understood, it's trying to understand, when a linear transformation is understood, it's trying to understand the two vector spaces, how they are created. That means, what are the vector spaces created? That means it's asking, we should explore what are the vector spaces attached to this linear transformation. And we'll understand those vector spaces. Rather, we can remove the linear transformation and we can express as a matrix. So we'll just therefore learn the matrix theory well now. No linear transformation. Actually, they're equivalent right now. So what we'll learn that what are the vector spaces attached to this matrix. So I will define those, and next day I will be doing the properties of those and understanding what is the linear transformation in entirety. Okay. Because some problems will be given like this, that find, and I will do one of these problems, find the kernel and find the range. So I will help you find them. Okay. So that's the idea. So what are the vector spaces attached to this matrix? The idea is that we have to understand the linear transformation in details, right? It's just not over when we just have the matrix form, because we don't know what is about matrix only. Just we transform the linear transformation theory to the matrix theory. Now we'll understand what is a matrix and how the matrix behaves, what the vector spaces attached to the matrix. So the vector spaces that attach to the matrix are the following: the four fundamental vector spaces. Null space of T, or we can also call the kernel of T, row space of T, column space of T, or the range of T, and the null space of A transpose, or the T transpose. So these four fundamental vector spaces we'll understand, and it will give a lot of entire good idea about the vector space, about the matrix, but not entirely. But we'll see it gives very good idea about how the matrix is behaving. Okay, at least with respect to the linear system of linear equations. With respect to system of linear equations. Let's sort of understand this. So the kernel is nothing but the set of, imagine a matrix. Okay, whenever I'm telling a linear transformation, imagine a matrix multiplication with a vector. The set of vectors x belong to R to the power n, or the domain T from R to the power n to R to the power m. Let's consider this only. So therefore the matrix of T is m cross n. Domain such that T of x is going to 0. That means it's going to 0, this matrix. The row space. The row space is nothing but, we have seen the column space, right? The column space is nothing but the set of all vectors that are in the range. That what are all vectors? If you take all the possible x in this, what are the all possible vectors this matrix is taking values in? This is a subspace of the R to the power m. Remember that, because it's like in the range of this. Row space of T is the set of all vectors. Okay. T transpose ka. Now T transpose is nothing but a function from R to the power m to R to the power n, right? Because the matrix will become m cross n. R to the power m to R to the power n. N cross m. The matrix will be n cross m. N cross m. N cross m. This is a Rm. This is a subset of R to the power, subspace of R to the power n. The row space is nothing but sort of all vectors x belong to R to the power m such that T transpose x vector is equal to, sorry. It's a set of all possible vectors T transpose is taking. R to the power m. And null space is nothing but also asking same thing, x belonging to R to the power n, m. Am I telling it right? 1 second. I think this will be R to the power m n, because it's taking n to, yeah. And this such that T of x is equal to 0. It's subset of R to the power n. So we're getting these four spaces. So it means the set of all vectors such that Ax or Tx is equal to 0, the matrix Tx is equal to 0. Set of all vectors such that all vectors of the form T transpose this, all vectors of the form. Here it's all vectors of the form this is T. Here it's all vector of the form such that this transpose this is equal to 0. So understand this is an r to the power m, this is an r to the power n. Okay. So these are the matrices attached to it. So I will give it I will give an exercise to you to show that these are all vector spaces. You can easily show it. I will show one for you. Let's check the kernel. All these are vector spaces. Or subspaces. Why? It's very simple. Let's take an example. Let's take null space of T. It's nothing but, let's take two elements, X and Y, which are belong to null space of T. You have to show that 0 belongs to null space of T, which is very obvious because T of 0 is 0. So it's obvious that this condition holds. Second is that T of alpha x plus y is nothing but what? Alpha. So you have to show what? This belongs to null space. So alpha x plus y also belongs to the null space. That means T of alpha x plus y belongs to the null space. Sorry, T of alpha x plus y is equal to 0. That you have to show, because this must also belong to null space. So this is, since T is a linear transformation, we get this. And since Tx and Ty are 0, this is alpha times 0 plus 0 is equal to 0. That means what? It implies that alpha x plus y belongs to null space of T. So therefore it's closed and this 0. Therefore this is a vector space. Okay. All of you understood this? This is a vector space. Shomya, did you understand? Shomya, did you understand? Okay, anyways. So thus we get is a vector space, and all you will prove that I will not do this problem because it will be therefore a waste of time. But all these are vector spaces, and these are the four fundamental spaces, and we'll see how this helps you to discover the set of all solutions. So now remember that our goal was to find the set of all solutions. So we'll see how these definitions, so null space of a linear transformation, row space, column space, and null space of T transpose. It's very fundamental to understand a solution system of linear equations, because system of linear equations is nothing but asking something very important. So next we will start with system of linear equations and these four subspaces and prove this. So this will be a homework also, that this is a vector space. Show that this is a vector space. This is the homework. So till today, so next day, that is tomorrow, I will start with showing that, with starting with system of linear equations and what this individually means, and this how this we can explore more about the, what all these things mean together. Okay. So also I will do one problem. I will start with this problem tomorrow. I'll start with this problem tomorrow. It's a different type of problem. Now think about this problem. I will start with this problem tomorrow. I will give it in the math group. I'll start with this problem tomorrow. Okay, so that's it, guys. So good night for today. I hope you enjoyed the class, and I will see you tomorrow with these examples on how we can explore this whole things together. linear transformation to very specific. Okay, so yep. So all the best, and I will see you tomorrow. Bye bye. Good night.